Is everyone ready? Let's get ready for chemistry! VSEPR theory starts with the Lewis dot structure, so you need to go through all the steps of finding the Lewis dot structure. So, the Lewis dot structure for carbon dioxide. The next step is to determine the steric number. Steric refers to things taking up space in space. Now, what takes up space in space? Sigma bonds and lone pairs of electrons. Now, carbon dioxide doesn't have any lone pairs of electrons on the central atom, so let's just look at the number of sigma bonds. The first bond in the double bond is a sigma bond, and then the second bond is the pi bond. So carbon dioxide has 2 sigma bonds. So the steric number here is 2. How do two things try to get as far away from each other as possible? It's valence shell electron pair repulsion. So electrons are traveling in pairs, and they're trying to repel each other because electrons always have a negative charge. But they're constrained by the central atom. So the electrons have to stay on the central atom, but they're trying to get away from each other. I can model this by tying a couple of balloons together and seeing what they do. So these balloons are going to do a great job of representing hybridized electron orbitals. So let's tie them together and see what shape they make. So the shape that they make is this. Two things trying to get as far away from each other as possible, orient themselves on either side of a line. We call this shape linear, and we call this bond angle 180 degrees, because it's 180 degrees from one molecule to the other. So this is linear, and then the bond angle here is 180 degrees. Okay, so far so good. Let's look at boron trifluoride. The first step is to draw the Lewis dot structure. Boron trifluoride doesn't meet the octet rule, but boron doesn't need to. Boron is happy having 6 electrons. After we have the Lewis dot structure, we want to figure out what the steric number is. The steric number is the number of sigma bonds and the number of lone pairs of electrons coming off of the central atom. Boron has 3 sigma bonds coming off of it, so the steric number here is 3. We want to know what shape 3 things getting as far away from each other as possible make. If you take 2 electrons and then you put another one on it, okay, so if you take 2 electron pairs and then you put another one on it, 3 hybridized orbitals trying to get as far away from each other as possible will make a shape that looks like this. Now, this shape is flat. We call this shape trigonal planar. Okay? So all of the electron pairs are all on the same plane. It's a little bit easier to see if I show you it like this. So this is trigonal planar, and then as you can see, all of the electron groups are located all on the same plane. So this molecule is flat. Now, this molecule is also symmetrical. You've got 3 electron groups, this one coming off this way, this one coming off that way, and this one going up. The lateralness of these 2 groups coming off to the side cancel each other out, and then these come down a little bit, and this one goes up a lot, and the downness of this cancels out the upness of that. We normally draw that using vectors. If the bond polarity is a vector, then it's going this way. If you take those vectors and you add them up by putting them nose to tail, they will add up to 0. They'll all cancel each other out. So this molecule is non-polar because it's perfectly symmetrical. It's the same thing with this one. If you look at the bond polarity in this molecule, but you add up the vectors in three-dimensional space, they will all add up to cancel each other out, so this molecule is nonpolar. Let's look at another one. The first thing you need to do is draw the Lewis dot structure. Now this would need resonance structures, and then it would need square brackets around the whole thing. The steric number is the number of sigma bonds and the number of lone pairs on the central atom. So 1 sigma bond, 2 sigma bonds, 1 lone pair, the steric number is 3. So we'll have 3 electron pairs trying to get as far away from each other as possible. Now we already know the shape for that, but this is a little bit different because of the lone pair. When you look at the nitrogen bonded to the oxygen, there's a nucleus here and there's a nucleus there, and in between there are electrons. Here there's a nucleus here, but here there's no nucleus on the other side of that pair of electrons. So this lone pair of electrons, this feels more negative. It's going to have a stronger repulsive force because there's no nucleus on the other side of it. What that's going to do is that's going to push these things away from it more, causing them to become closer together. The other thing that's going to do is the lone pair of electrons is a wave function. It doesn't take up any space in three-dimensional space. It's pushing the other electron pairs away from it, so it looks like it is. But if you were to look at this under a microscope somehow, you wouldn't see the lone pairs. So when we talk about the molecular geometry, we talk about the lone pairs as if they were invisible. The steric number is determined by looking at all of the sigma bonds and electron pairs, but the molecular geometry is determined by looking at just the bonded atoms. Now you start with the steric number. A steric number of 3 is trigonal planar. But with one lone pair hiding, it's no longer trigonal planar. We call this shape bent because it looks like the atoms are bent. It's not a 180 degree angle. So the bond angle here is 120 degrees. With the lone pair of electrons, this lone pair of electrons is pushing these groups closer together, so the bond angle is less than 120 degrees. If one of these is a lone pair of electrons, it's going to push the other 2 electron groups closer together, making the bond angle between the 2 bonded atoms smaller. So the bond angle between these 2 oxygens is smaller than 120 degrees because this electron lone pair is pushing those 2 sigma bonds away from it more than they're all pushing each other away. The lone pair has a greater repulsive force. Normally you would just write it like this. It's less than 120. The important thing to note here is that this shape is always polar. It's an asymmetrical shape. If you look at the bond polarities here, they're going to add up to give you something that definitely has a net pole one direction. So this side of the molecule will be kind of positive, and this side of the molecule will be kind of negative. With a steric number of 3 and 1 lone pair on the central atom, the shape of this is bent. With a steric number of 3 and no lone pairs on the central atom, the shape of this is trigonal planar. And the bond angles here, the bond angles are 120 degrees. Let's look at carbon tetrachloride. Carbon tetrachloride has 4 sigma bonds and 0 lone pairs. So the steric number here is 4. And as you can see, 4 things trying to get as far away from each other as possible orient themselves on 4 things trying to get as far away. 4 things trying to get as far away from each other as possible orient themselves on the edges of a clover. Dagnabbit. Yeah, okay, so it's definitely not a clover, and it's definitely not a flat shape. We call this shape tetrahedral. You can see it's a 3-dimensional shape. That's perfectly legal because atoms exist in 3-dimensional space. So this shape is called tetrahedral. It's going to look something like this. Now, this shape is not a flat shape. This shape exists in 3-dimensional space. But it is perfectly symmetrically rotational, or it would be if I had managed to do this correctly. Get my bond angles correct here. But this is a perfectly symmetrical shape as long as all of the outside atoms are all the same. If you want to know the bond angle between any 2 of these atoms, and this is a number that you can't really rederive, you're just going to have to remember it. The bond angle between these 2 atoms is 109.5. So some mathematician figured that out. This is 109.5, the bond angles between the sides of a tetrahedron. So if the steric number is 4, the shape is tetrahedral. The way we would draw that would be like this. So the wedge means the atom is coming out of the paper, and the dashed line means the atom is going backwards into the paper. Then this bond angle is 109.5, and that's very important. It's very important that you remember that. Now, I'm not going to show you how all of the vectors add up, but they do. All of the vectors cancel each other out. This molecule is perfectly symmetrical. It will be nonpolar. Will it always be nonpolar? It will if the outside atoms are all the same. If the outside atoms are all the same, then the vectors will cancel each other out, and the molecule will be nonpolar. It's not if it is polar, it's not the geometry's fault. Or it is the geometry, but it's because all the outside atoms are different. Let's do another one. Classic example, ammonia. Ammonia has 3 sigma bonds and 1 lone pair. So the steric number here is 4, but one of those is a lone pair. So first of all, that lone pair is going to push all of the other atoms away from the lone pair, causing those bond angles to be smaller. Normally, this bond angle here would be 109.5, but the bond angle is going to be smaller because the unconstrained lone pair is going to push those bonded atoms away from it more. But also, you have a tetrahedral shape, but one of them is a lone pair. If one of them is a lone pair, it's hiding, it's invisible. And you can see the shape is no longer symmetrical. Their lateralness is all canceling each other out, but they're all going down a little bit. They used to be canceled out by this one going up a lot. But if this one's gone, they're not being canceled out. The shape is no longer symmetrical. Now, this shape is a 3-sided pyramid. It's 3-sided, but it's not flat. So we call this shape trigonal pyramidal, in that it's a 3-sided pyramid. You know, because it's got 3 sides, not the base. The base doesn't count. Because of that asymmetrical lone pair of electrons, this shape is always polar. And you can take that to the bank. There's no way to rearrange the atoms to make this shape polar. It's always asymmetrical. It's always polar. The even more classicaler, that's not a word, classicaler example than ammonia is water. A lot of students will draw water like this. And if you draw water like this, it looks nonpolar. But that's not how you determine molecular polarity. There's 2 sigma bonds, and then there's 2 lone pairs of electrons. Now on paper, you're like, oh yeah, look, they all cancel each other out. Yay, we're great, hurrah! But no, that's not how you do this. Remember that this molecule exists in 3-dimensional space. So the base shape is tetrahedral. Let's go look at it. The tetrahedral shape looks like this. But if 2 of them are lone pairs, 1, 2, the shape that you're left with is bent. It's not symmetrical at all. And there's no way that you can rotate this shape that's going to make it symmetrical. So when you have a steric number of 4 and 2 of them are lone pairs, the shape that you get is bent. This bond angle started out as 109.5, but with 2 lone pairs pushing each other, this bond angle is going to be even smaller than 109.5. So with a steric number of 4, you would start with a tetrahedral shape, but your molecular geometry would be bent. It's not linear at all. It would be better to draw it like this. And then this bond angle starts out as 109.5, but it's actually going to be less than that. And the 2 electron lone pairs compound the effect. So it's less than 109.5, like 105 or something like that. Now this molecule isn't symmetrical at all. It's not nonpolar. It's not nonpolar. It's not nonpolar. It's polar. It's always polar. A bent geometry is always polar. That's important for water. It gives it all kinds of properties. Here's where things start to get really exciting. Phosphorus pentabromide looks like this. With 5 sigma bonds, the steric number here is 5. 5 things trying to get as far away from each other as possible are going to make kind of a zany kind of shape. If I take 2 things and I add 3 things, 2 plus 3 is 5 things. 2 plus 3 is a steric number of 5. And it's good that I'm using different colors for these because you can clearly see what this shape looks like. 2 things plus 3 things makes 5 things. Actually, it still makes 2 things and 3 things. If you look at this, you can see you've got the trigonal planar. The green balloons are trigonal planar. And then the pink balloons are linear. So 5 things is linear plus trigonal planar. Now we don't call it linear plus trigonal planar. We call it trigonal bipyramidal. Then the first time I say that name, all the students are like, and they're like melting. But I challenge you to come up with a more descriptive name than trigonal bipyramidal. A name that describes this shape without you ever have seen it. You probably can't. And I know what you're thinking. You're thinking, yeah, but trigonal bipyramidal doesn't describe this shape anyway. Well, if you dig into it a little bit, it does. You can see that you've got 1, 2, 3-sided pyramid on top, and then on the bottom, you've got 1, and on the bottom, you've got 1, 2, 3-sided pyramid on the bottom. So you've got 2 3-sided pyramids sitting on top of each other, trigonal pyramidal, and there's 2 pyramids, so trigonal bipyramidal. Now this one actually has 2 different bond angles. The bond angle between the green and the pink, it's hard to see with the balloons, but the bond angle between the green and the pink is 90 degrees. the bond angle between the green and the green is 120 degrees. So trigonal bipyramidal, the molecules in the middle are trigonal planar, and then there's the top and bottom molecules. Now, it's important to differentiate between the two. I'll explain why in a second. But this is what your shape looks like. So there's two bond angles. There's the 120 degree bond angle from the trigonal planar part of it, and then there's the 90 degree bond angle from the linear portion of the shape. So there's the 120 degree bond angle from the trigonal planar portion, and then there's the 90 degree bond angle from the linear portion meeting the trigonal planar portion. So this shape is called trigonal bipyramidal, and the bond angle is 120, but also 90. A better way to draw it would be like this. Trigonal bipyramidal. The bond angle here is 120, and the bond angle here is 90. You're just going to have to believe me. With all the outside atoms the same, this molecule is nonpolar. This molecule is symmetrical. The trigonal planar molecules all cancel each other out. And then the linear molecules all cancel each other out. So everyone cancels each other out. Excepting, of course, when they don't cancel each other out, like when you have different outside atoms or when you have lone pairs. Does this one have a lone pair? You won't know until you draw the Lewis dot structure. Oh, a lone pair! Run for your lives! So the sigma bonds to the fluorines count, and then the lone pair on the sulfur counts. So the steric number here is 5. That means a trigonal bipyramidal shape. It also means that atoms are pushed away from each other. But with the lone pair, one of the atoms is now hiding because it's not an atom, it's just a pair of electrons. That changes the geometry. Now, if you start with a trigonal bipyramidal shape, and then you take away one of the bonded atoms, well, wait a second. If I take away the top atom, that makes a trigonal pyramidal shape. But if I take away one of the trigonal planar atoms, that doesn't make a trigonal pyramidal shape. So which one is it? Because you would get two different shapes depending on which one you took off. Where is the lone pair? We use specific terminology to refer to this shape. We talk about the axial positions, and we talk about the equatorial positions. The equatorial positions are the trigonal planar atoms. The axial positions are the linear atoms. So the axial positions are the linear atoms, the pink balloons. The equatorial positions are the green balloons. Okay? So the green balloons are equatorial, the trigonal planar balloons are equatorial, and then the linear balloons are the axial. Very important then, where is the lone pair? The lone pair has a greater repulsive force, but doesn't actually occupy space. It's the nucleus of the atoms, it's the nucleus of the bonded atoms that occupy space. So when you look at this, you look at the molecular geometry of this, the electrons are going to orient themselves in such a way to minimize steric hindrance. Not to minimize repulsive forces, but to minimize atoms trying to occupy the same space. That means the electrons are going to be located on the equatorial positions. Okay? So electron lone pairs are always occupying equatorial positions on a trigonal bipyramidal shape. So this is not trigonal pyramidal, this is seesaw. So the name of this shape is called seesaw because it kind of makes a little seesaw. And I know children are not allowed to play outside anymore, but back in the day, they used to have this thing where one kid would sit on one side and the other kid would sit on the other side, and they'd like jump up and down and they'd seesaw. Well, that's what this is. So the name of this shape is called seesaw. That's the legitimate name of this shape. This shape is seesaw. The electron lone pair here is pushing all of the bonded atoms away from it. So the molecular geometry is seesaw. To look at the bond angles, it would be easier to just redraw the shape. This bond angle would normally be 90, but the electrons are pushing it away, so it's less than 90. And these would normally have a bond angle of 120, but the lone pairs are pushing it away, so it's less than 120. Because this shape is asymmetrical, it will always be polar. There is never a time when this molecule is not polar. With that pair of electrons there, this molecule is always going to be polar. Let's do another one. Now, in order to not be surprised by whether there's lone pairs of electrons or not, you have to draw the Lewis dot structure. You normally can't just look at a formula and figure out what the geometry is. The only way you can do that is if you've already drawn the Lewis dot structure some other time and you remember what it looks like. Now, I pretended not to know what I was doing when I was drawing it. If you look at the way I've drawn it, this is totally misleading. You would think, that by the way that I've drawn it, that it's trigonal planar. But that's not how this works. You've got to picture the thing in three-dimensional space and figure out where everything would be. First, we start with the steric number. With 3 sigma bonds and 2 lone pairs, the steric number here is 5. But 2 lone pairs are going to change the base shape into something different. So normally it would start out as trigonal bipyramidal, but now there are 2 lone pairs of electrons. Now, where do those lone pairs of electrons orient themselves? They orient themselves on the equatorial positions. Both pairs of electrons will orient themselves on the equatorial positions. So the first lone pair of electrons on the equatorial position, and then the second lone pair of electrons on the equatorial position makes a T. It looks like a T. Not the like, let's drink tea kind of tea, but it's like the letter T. It's a T. So the name of this shape is called T. T-shaped. This is T-shaped. A very descriptive name, kind of a silly name. Not more silly than seesaw, though. So this shape is T-shaped. With the electron lone pairs pushing away the bonded atoms, this angle would normally be 90 degrees, but this is all getting mushed together, so it would be less than 90 degrees. So it's better to redraw this to be representative of what's actually happening. This bond angle here is normally 90 degrees, but the 2 lone pairs pushing it away, it's less than 90 degrees. Maybe it's 86 degrees. Who can say? This will always be an asymmetrical molecule, so it will always be a polar molecule. T-shaped molecules are always polar molecules. So if you have a steric number of 5 with 2 lone pairs of electrons on the central atom, it's T-shaped and it's always polar. But Mr. Comer, noble gases don't form bonds. Yeah, well, fluorine gets what fluorine wants. Ah, it's hideous. Cast off your preconceptions that you just concepted because I made you concept them. With a steric number of 5 and 3 lone pairs, we're going to start with a trigonal bipyramidal geometry. So trigonal bipyramidal geometry, the lone pairs would orient themselves on the equatorial positions. 1, 2, 3. Trigonal bipyramidal with 3 lone pairs, the shape is linear. If the outside atoms are the same, then this is a nonpolar geometry. The bond angles here are 180 degrees. So the name of this shape is linear. The bond angle here is 180 degrees. It's not less than 180 because all of the lone pairs are canceling each other out. And the shape is a nonpolar symmetrical geometry. Let's look at something with a steric number of 6. With 6 sigma bonds, sulfur hexafluoride has a steric number of 6. 4 things plus 2 things will make 6 things. This shape is called octahedral. Now, that throws a lot of students off at first because it's got a steric number of 6. Why should it be called octahedral? But the same thing with tetrahedral. This is an 8-sided polyhedron. This shape has 8 identical sides. If you've ever played tabletop dice games, this is a D8. So if you look, you've got 1, 2, 3, 4 sides on top, and 1, 2, 3, 4 sides on the bottom, and all 8 sides are all identical. It's an octahedron. The bond angles on my octahedral shape are all 90 degrees. And it doesn't matter which way you rotate it, it's all rotationally symmetrical. All of the bond angles are all 90 degrees. Because it's a perfectly symmetrical shape, an octahedral shape is nonpolar, provided that all of the bond polarities cancel each other out. And the bond angle here is 90 degrees. With 5 sigma bonds and 1 lone pair of electrons on the central atom, the steric number is 6. And let's look at how the geometry changes when you add in that lone pair of electrons. Starting out with a steric number of 6, we have 1 lone pair. Now there's no axial or equatorial positions for octahedral because it's a perfect polyhedron. So we'll just take one of them off. That leaves an asymmetric geometry. The electrons are no longer perfectly canceling each other out. This makes a pyramid with a square base. So this shape is called square pyramidal. It's an asymmetric shape. Now because the lone pair is not being balanced out by anything else, its repulsive forces are greater, so it's pushing these bond angles closer together. So while this used to be 90 degrees, it's actually less than 90 now. So the shape is called square pyramidal. The bond angle here is less than 90 degrees, and it will always be a polar geometry. So if you have this shape, it will always be polar. With 4 sigma bonds and 2 lone pairs, the steric number here is 6. Now, what happens when you have 2 lone pairs on this? I hope by now you've given up looking for patterns. The best way to determine the pattern is to simply picture it in your mind and see it in your mind. Otherwise, you're going to have to remember everything. There are no patterns. Okay, so with 2 lone pairs, we'll take one off from anywhere. That gives us square pyramidal. And then where is the next electron lone pair located? It would be located on the opposite side. So if one lone pair is located over here, then the other lone pair would be located perfectly opposite of it. You'd be left with a shape that looks like this. This shape is square planar. So square and planar as in flat. It's very important the shape is flat. Now, the electron lone pair on the top is canceling out the electron lone pair on the bottom, so this shape is symmetrical. And the bond angles here, because the lone pairs are canceling each other out, the bond angles are exactly 90 degrees. The shape is square planar. The bond angles are exactly 90 degrees. And this is a non-polar geometry. Now, we could talk about what happens if you have a steric number of 6 with 3 lone pairs, a steric number of 6 with 4 lone pairs. I've never seen an example of that, but let's go look at it anyway. Steric number of 6, octahedral. 1 lone pair. Square pyramidal. 2 lone pairs. Square planar. 3 lone pairs, T-shape, and this would be polar because it's asymmetrical. 4 lone pairs, linear, and this would be a non-polar shape. So if you were to have a steric number of 6 with 4 lone pairs, then you would have a linear geometry. Is everyone ready? Let's get ready for chemistry! Four things trying to get as far away from each other as possible orient themselves on the edges of a clover. Land of the balloony woonies. Like my fat camera. Special angle for making me look fat.